In this video, we're going to take our discussion of double displacement reactions one step further and talk about writing net ionic equations. A net ionic equation is an abbreviated or simplified chemical reaction equation that shows us specifically and exclusively only those substances that participate in a chemical change. In a double displacement reaction that produces a precipitate, for example, not necessarily all of the ions that are floating around in solution contribute to making a precipitate. To write a net ionic equation, we're going to write firstly an overall equation that has everything incorporated into it, identify phases, balance that equation, and then recognize which substances break apart into respective ions and which don't on the basis of solubility. Any ions that aren't changed from one side of a reaction to another, in this case, are known as spectator ions and can be eliminated from the overall equation to leave us with just those ions that participate in a chemical change. For example, if we mix together solutions of sodium hydroxide and magnesium chloride, what can we predict about their reaction, and then how can we write a net ionic equation that describes just the chemical change that's happening when we mix these two substances together? Sodium hydroxide consists of a sodium cation that's got a +1 charge, a hydroxide anion with a -1 charge. That means that sodium hydroxide's chemical formula can be written as NaOH, one of each ion. According to our solubility rules, hydroxides are soluble when they're with group 1 cations. Sodium is a group 1 cation, so this must be an aqueous solution. Magnesium chloride consists of magnesium, that's Mg with a 2+ charge, and chloride, that's Cl-. The chemical formula for magnesium chloride in our chemical reaction must therefore be MgCl2. Chlorides are soluble except when silver, mercury, or lead are present with those. And so we should expect magnesium chloride to likewise be in the aqueous phase. As these things react, we can now expect a double displacement reaction. Our cation in our first compound is sodium, our anion is hydroxide. Our cation in the second compound is magnesium, our anion is chloride. In other words, sodium and chloride and magnesium and hydroxide will get together after sodium hydroxide and magnesium chloride swap partners. We're going to expect this exchange of ions. Cation A, anion D, cation C, anion B get together. The result is that we make, firstly, sodium chloride. Sodium is a +1 cation, chloride is a -1 anion. We should predict that the compound that forms if those two ions get together is NaCl. According to our solubility rules, this must be an aqueous or soluble substance because chlorides are only insoluble, again with silver, mercury, and lead. The other substance that forms comes from magnesium hydroxide. Magnesium with a 2+ charge and hydroxide with a -1 charge getting together. This chemical formula must be represented by MgOH2. We'd need 2 hydroxide ions for every 1 magnesium cation. According to our solubility rules, hydroxides are only soluble if they're with heavy group 2 elements like calcium on down. Magnesium is not one of those heavy group 2A elements, and so we would expect magnesium hydroxide to be insoluble or precipitate as a solid when we react sodium hydroxide and magnesium chloride with each other. From here, we can balance this overall reaction. We can show a coefficient of 2 in front of sodium chloride to balance chlorines, and a coefficient of 2 in front of sodium hydroxide to balance sodiums. This coefficient also balances the hydroxides from one side of our reaction arrow to the other. So we are now balanced, and we have phases associated with every one of our substances. In the reactants and the products, we predicted our products by being able to swap partners. Sodium gets with chloride, magnesium with hydroxide. From here, we're going to do a few more steps to look at a net ionic equation. The first thing that we're going to do is break up anything that's soluble into its respective cations and anions, because sodium hydroxide doesn't exist as an intact molecule. It exists as cations of sodium and anions of hydroxide. Magnesium chloride doesn't exist as an intact molecule. It exists as cations of magnesium, anions of chloride. To show that, let's write on another line the ions that make any soluble compound. Here we're going to separate anything that's in the aqueous phase into its respective ions, because in solution, these ions will be the thing that are mixed up and moving around, not molecules as a whole, unless we've got a solid or other phase associated with the compound. So anything that's aqueous, we're going to break up into its component ions. Sodium hydroxide is soluble. It's in the aqueous phase. It exists as sodium cations and hydroxide anions in solution. The coefficient of 2 carries down to each one. 2 sodium cations and 2 hydroxide anions are produced in solution every time we mix 2 moles worth of sodium hydroxide ionic compound with water. Then in a similar vein, because magnesium chloride is also soluble, it exists as magnesium cations with a 2+ charge and 2 chloride anions with a minus charge each. The reason for this 2 here is that there are 2 chlorides in every formula unit of magnesium chloride. On the opposite side of this arrow, because sodium chloride is soluble, it really exists as sodium cations and chloride anions, again carrying a coefficient of 2 down in front of each because of their balanced equation. The only thing that won't change or be broken up into its respective ions is magnesium hydroxide. That's because this thing is explicitly shown to be a solid precipitate. This does exist as an intact molecule and does not separate into its ions when mixed with water. So the real chemical picture for what magnesium hydroxide looks like is just precisely this formula intact as it is. Notice that on the left-hand side of our reaction, we have 2 sodium cations in aqueous solution. And on the right-hand side of our reaction now, we also have 2 sodium cations in aqueous solution. Sodium has not changed form chemically from start to finish. That means that sodium really didn't react at all. Anytime we see the same thing on opposite sides of a reaction arrow in a chemical reaction, just like when we see things that are the same on opposite sides of a mathematical equation, those things can cancel out. Similarly, we see 2 chloride anions on the left-hand side of our reaction arrow, 2 chloride anions on the right-hand side. These chlorides, likewise, did not change from start to finish in this chemical process. They cancel out as well. In fact, anything that cancels out is really just along for the ride. It's there to bring the ions together that do the reacting in the first place. In effect, sodium and chloride in this reaction are just watching other materials react or change chemically. We call these ions that can be canceled out spectator ions, because their purpose is really just to bring together those substances that do chemically transform. In this reaction, anything that's left over is part of a net ionic equation that shows us precisely what and how a chemical change has occurred. Those reacting substances are 2 hydroxide anions and 1 magnesium cation, getting together to make the solid precipitate magnesium hydroxide, MgOH2. These substances constitute the actual chemistry that has happened when we mix sodium hydroxide and magnesium chloride solutions together, and this reaction is what we refer to as a net ionic equation, showing only those substances involved in a chemical change and excluding spectator ions, those things that were just along for the ride. Let's look at a second example. Suppose that we mix solutions of hydroiodic acid and zinc nitrate together. Can we write a net ionic equation for what happens here? Firstly, let's predict what the products would be as we mix these things together, and then treat the results with the same process that we used in the previous example. Hydroiodic acid has a name suggesting that this acid does not contain oxygen. It must contain a hydrogen cation and an iodide anion. The formula for hydroiodic acid therefore must be HI. Acids are always an aqueous solution. Zinc nitrate has a cation zinc, which always gets a 2+ charge, and nitrate, which has the formula NO3-. To write the formula for zinc nitrate, then, we'll need 2 nitrates for every 1 zinc, ZnNO3, 2. Nitrates are soluble, so zinc nitrate should be as well. As we swap partners in this double displacement reaction, hydrogen and nitrate can get together, H+ and NO3, to make nitric acid, HNO3. Acids are always aqueous. Separately, zinc and iodide can get together to make ZnI2. We need 2 I's for every 1 zinc to balance charge. According to our solubility rules, iodides are soluble except when silver, mercury, or lead are present, and since zinc is neither silver nor mercury nor lead, this must be soluble or aqueous. From here, we can balance our equation. We'll need a coefficient of 2 out in front of our hydroiodic acid. We'll need a coefficient of 2 in front of our nitric acid to balance everything out. Next, anything that's soluble can be broken up into its respective ions because, as virtue of being soluble, these things exist not in their intact form, but in their ionic form. Hydroiodic acid is a strong acid. It will break up into H+ cations and I- anions. Again, I'm carrying through the coefficient that was in front of the original molecule in the top balanced reaction. Zinc nitrate is soluble. It dissociates into zinc 2+ cations and 2 nitrate anions. Nitric acid is soluble. It's a strong acid. It will be broken up into 2 hydrogen cations, 2 nitrate anions. And lastly, zinc iodide is soluble. It splits up into zinc 2+ and 2 iodide anions. Now, just like before, we can look for things that are identical on either side of a reaction arrow. We have 2 H+, they can go away, they are spectator ions. We have 2 I-. We have a zinc 2+ on both sides. We have 2 nitrates on both sides. So look at that. Everything is canceled out. Everything is a spectator ion, meaning there's no chemical change. There's no difference between our starting materials and our products, and so we would not expect to see any result from mixing these 2 solutions of hydroiodic acid and zinc nitrate together. Another way to put this is when asked for a net ionic equation for this reaction, we'd predict no reaction whatsoever.